Good day, class. This is Sir Otep, and welcome back to our e-classroom. The universe is everything, from the tiniest particles to the largest galaxies, and even the very existence of space, time, and life. But have you ever wondered, what is the origin of the universe? If you do, then this is the day that you will learn about it. The origin of the universe is the origin of everything. Multiple scientific theories, plus creation myths from all around the world have tried to explain its mysterious beginning. However, the most widely accepted explanation is the Big Bang Theory. The Big Bang Theory, developed by George Lemaitre in 1931, states that the universe began as a hot and infinitely dense point or very tiny ball of energy that is only a few millimeters wide. About in between 13 to 14 billion years ago, this tiny singularity or ball violently exploded. And it is from this explosion or bang where matter, energy, space, and time were created, or the start of everything. The Big Bang model is supported by a number of important observations, such as the abundance of light elements, hydrogen, helium, and lithium. Second, the cosmic microwave background radiation. And third, the expansion of the universe. Although the Big Bang Theory tries to explain the origin of the universe, but this theory has puzzles or problems that were not properly addressed before. That is why there were several theories created and made by scientists to explain those problems. And here are some of the theories that tries to explain the origin of the universe. The expanding universe theory. This theory was actually conceived earlier than the Big Bang theory. It was developed in the late 1920s by the American astronomer Edwin Hubble. Edwin Hubble made a very interesting and important discovery. Hubble made observations that he interpreted as showing that distant stars and galaxies are receding from Earth in every direction. Moreover, the velocities of recession increase in proportion with distance, a discovery that has been confirmed by numerous and repeated measurements since Hubble's time. The implications of these findings is that the universe is expanding. Hubble's hypothesis of an expanding universe leads to certain deductions. One is that the universe was more condensed at a previous time. From this deduction came the suggestion that all currently observed matter and energy in the universe were initially condensed in a very small and infinitely hot mass. A huge explosion known as the Big Bang then sent matter and energy expanding in all directions. The inflation theory. Another theory developed around 1980 by Alan Guth, Andrew Lind, Paul Steinhardt, and Andy Albrecht. This theory was conceived to answer several problems with the standard Big Bang theory, such as the flatness problem.
The WMAP,
or the Wilkinson Microwave Anisotropy Probe, a NASA Explorer mission launched on June 2001 to study the properties of our universe and determined that the geometry of the universe to be nearly flat. However, under the Big Bang cosmology, curvature grows with time. A universe as flat as we see it today would require an extreme fine-tuning of conditions in the past, which would be an unbelievable coincidence. Inflation theory answered this problem by proposing that there was a period of extreme extremely rapid or exponential expansion of the universe prior to the more gradual Big Bang expansion, during which time the energy density of the universe was dominated by a cosmological constant type of vacuum energy that later decayed to produce the matter and radiation that fill the universe today. Inflation was both rapid and strong. It increased the linear size of the universe by more than 60 e-folds, or a factor of 10 to the 26th power, in only a small fraction of a second. Inflation is now considered an extension of the Big Bang theory since it explains the above puzzles so well, while retaining the basic paradigm of homogeneous expanding universe. Steady-state theory. This theory was first put forward in 1948 by British scientists Sir Hermann Bondi, Thomas Gould, and Sir Fred Hoyle. Steady-state theory views that the universe is always expanding but maintaining a constant average density, with matter being continuously created to form new stars and galaxies at the same rate that the old ones become unobservable as a consequence of their increasing distance and velocity of recession. A steady-state universe has no beginning and no end in time. And from any point within it, the view on the grand scale, such as the average density and arrangement of galaxies, is the same. The oscillating universe theory. This theory was first proposed by Albert Einstein in the 1920s in response to the expanding universe model. The oscillating universe theory is a cosmological model that combines both the Big Bang and the Big Crunch as a part of a cyclical event. That is, if this theory holds true, then the universe in which we live in exists between a Big Bang and a Big Crunch. In other words, our universe can be the first of a possible series of universes, or it can be the nth universe in the series. Those are some of the theories that try to explain the origin of our universe. Though there are several theories about our universe, there are two things that are seemingly true to all of these theories that I have shared to you. One is that the universe is from a tiny entity and exploded. And two, the universe is expanding. With all these theories and all these discoveries and all this information, we have now a modern explanation of how our universe as we see today came to be. Of course, following the standard of the Big Bang theory. To give us more information and to learn more, please watch this video clip from the National Geographic.
The universe began as a hot and infinitely dense point. Only a few millimeters wide, it was similar to a supercharged black hole. About 13.7 billion years ago, this tiny singularity violently exploded. And it is from this explosion, this bang, that all matter, energy, space, and time were created. What happened next were two major stages of the universe's evolution. Called the radiation and matter eras, they're defined by key events that helped shape the universe. First came the radiation era, named for the dominance of radiation right after the Big Bang. This era is made of smaller stages, called epochs, that occurred within the universe's first tens of thousands of years. The earliest is the Planck epoch. No matter existed in the universe at this time, only energy and the ancestor to the four forces of nature, the superforce. At the end of this stage, however, a key event occurred in which gravity split away from the superforce. Next came the Grand Unification epoch, named for the three remaining unified forces of nature. This epoch ended when one of those forces, called strong or strong nuclear, broke away. Then, the inflationary epoch began, during which the universe rapidly expanded. Almost instantly, it grew from the size of an atom to the size of a grapefruit. The universe at this time was piping hot, and it churned with electrons, quarks, and other particles. Then came the electroweak epoch, when the last two forces, electromagnetic and weak, finally split off. During the next stage, the quark epoch, all of the universe's ingredients were present. However, the universe was still too hot and dense for subatomic particles to form. Then, in the hadron epoch, the universe cooled down enough for quarks to bind together and form protons and neutrons. In the lepton and nuclear epochs, the radiation era's last two stages, the protons and neutrons underwent a significant change. They fused and created nuclei. And in doing so, they created the first chemical element in the universe, helium. The universe's new ability to form elements, the building blocks of matter, cued the matter era. Much as the name suggests, the matter era is defined by the presence and predominance of matter in the universe. It features three epochs that span billions of years, the vast majority of the universe's lifespan, and includes the present day. The first was the atomic epoch. In this stage, the universe's temperature cooled down enough for electrons to attach to nuclei for the first time. Called recombination, this process helped create the universe's second element, hydrogen. This hydrogen, along with helium atoms, dotted the universe with atomic clouds. Within the clouds, small pockets of gas may have had enough gravity to cause atoms to collect. These clusters of atoms, formed during the galactic epoch, became the seedlings of galaxies. Nestled inside those galaxies, stars began to form. And in doing so, they cued the latest and current stage of the universe's development, the stellar epoch. The formation of stars then caused a tremendous ripple effect and helped shape the universe as we know it. Heat within the stars caused the conversion of helium and hydrogen into almost all the remaining elements in the universe. In turn, those elements became the building blocks for planets, moons, life, everything we see today. This ecosystem of everything was only possible because of the many stages in the universe's development. While countless questions about the origins of our universe remain, it's only a matter of time for some long-sought answers to emerge.
And that's it, class. I hope that you learned something today. See you on our next e-class. Stay safe.